Hello everyone, so today we have a question regarding a little bit of calculus actually. We're obviously going to learn a little bit about integration, but we also have this Taylor and Maclaurin series, which is kind of going to be the takeaway from this video. And obviously we have a summation, a little bit of a double sigma kind of a question. So yeah, let's hope you learn something from it. This is the problem number B6 on the Putnam exam in 2016. So last problem of the day. Quite interesting actually, it's quite interesting. And in this video, you're going to be learning about Taylor and Maclaurin series, what the expansions of ln x, ln2 and ln1 plus x are, summations and integrals. After that, we have infinite geometric sequences, integration by parts. And after that, we have some book sessions of college mathematics. And at the end, a similar well challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so let's begin. So we need to evaluate this given sum over here. Now, before we maybe jump onto this problem, let's maybe discuss a little bit about what this Taylor series is, right? This Taylor series is something that is worth talking about. So Taylor series is essentially giving the polynomial expression for any real function. So for example, let me just give you a practical example of this. E raised to the power x can actually be written as 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus x raised to the power 4 by 4 factorial and so on and so forth. This keeps on going, right? Essentially, what is this? This is just a polynomial expression for e raised to the power x, and e raised to the power x can be kind of approximated like this, right? That actually helps with integration as well. You know, if you want to integrate e raised to the power x, you can just integrate this entire expression. Maybe like the first 3 or 4 terms, and that would give you a decent idea of what the integral might be. Very useful in definite integration especially. So to be more specific, this is the Maclaurin series, okay? This is actually the Maclaurin series. And Maclaurin series is nothing but the Taylor series about a is equal to 0, where a is called the center. That's just kind of like a brief overview of it. Now maybe let's just discuss in a little bit of detail. Okay, so what's the Taylor series? So like I was saying before, Taylor series is a method to represent any given function f in terms of a polynomial. So for example, e raised to the power x, ln x, ln1 plus x, all of these things, sine x, any of these trigonometric functions, any of these exponential function, logarithmic function, if you want to express them as a polynomial like we are doing over here, the Taylor series and more practically the Maclaurin series is a great way to do that. And how do you do that? Well, that's just a formula, just a simple formula for the Taylor series, and that is f of x is the summation from n is 0 to infinity of fn of a divided by n factorial times x minus a raised to the power n. And this fn of a is nothing but the nth derivative evaluated at x equals to a. So this is essentially the formula for f of x, and you don't have to remember this. What you do have to remember is something that's a little bit easier to remember. So once you expand this sigma, you will get f of x is equal to f of a plus f prime a times x minus a, okay, plus f double prime a divided by 2 factorial times x minus a whole square plus f triple prime a, which is the third derivative evaluated at x equal to a, divided by 3 factorial times x minus a whole cube, and this goes on and on and on and on. So you kind of need to remember this, and this it's just quite easy to remember honestly. You have f of x equal to f of a, then you take its derivative and multiply it by x minus a. You take its double derivative, multiplied by x minus a whole squared, and then remember that you have a 2 factorial in the denominator. And this is kind of like recursive, right? You have 3 factorial next, after that we'll have 4 factorial, fourth derivative, and then x minus a to the power 4. It's pretty simple actually to kind of like remember this after a few tries. And when you evaluate this at a is equal to 0, gives us the Maclaurin series, okay? Maclaurin series, right? Which was what I was talking about earlier. So at a is equal to 0, get a Maclaurin series. So what is the Maclaurin series? It's nothing but f of x will be f of 0. I'm just plugging in a is equal to 0 over here, plus f prime 0 times x plus f double prime 0 divided by 2 factorial times x squared plus f triple prime 0 divided by 3 factorial times x cubed and so on and so forth, right? Yes, that's pretty cool. this is the formula for the Maclaurin series, and practically we use Maclaurin series more than Taylor series, because A is equal to 0, which is A is called the center of the series. Basically, that is the more practical. Maclaurin series is just a more practical usage of it. And what I wrote over here of e raised power x, this is nothing but the Maclaurin series. Indeed, it's evaluated. It's just the evaluation of the Taylor series at A is equal to 0. Okay, great. So let's maybe take some examples, right? Examples. The first example that I mentioned to you earlier as well, I'm maybe going to take ln of 1 plus x, and I'm going to maybe try and formulate a polynomial expression for that. So what's the formula? And obviously I'm going to make the Maclaurin series at a is equal to 0, obviously. So what is f of x? F of x is ln 1 plus x. What is f of a? F of a is obviously at x equals to 0, right? There will be ln 1, which is 0, right? What is f prime x? It is 1 by 1 plus x. What is f prime a? It will be 1, right? X equal to 0. What will be f double prime x? It will be negative 1 divided by 1 plus x whole square. And what will be f double prime of a? It will nothing be negative 1. So when I plug all of this back into this equation, maybe, so what is, or maybe like just this equation, right? So what is f of x? We need to write down the Taylor series formula again. It's nothing but f of a plus f prime a times x minus a plus f double prime a times x minus a whole square divided by 2 factorial and so on and so forth. Right, now when I just plug this back over here, the data that I have, I'll get f of x equal to f of a. F of a was ln 1, this is equal to 0, plus f prime a. F prime a was 1 times x minus a, which is x, plus f double prime a, which was negative 1, divided by 2 factorial times x squared, and so on and so forth. So f of x, what was this? ln 1 plus x. So indeed, we get the fact that ln 1 plus x is nothing but x minus x squared by 2 factorial, and this just goes on and on. You will get the third term as x cubed by 3 factorial, you will get the fourth term as negative x cubed over 4 by 4 factorial, and so on and so forth. It's kind of like a repeating sequence: positive, negative, x squared, x cubed, x4, 1 factorial, 2 factorial, 3 factorial, 4 factorial. It's kind of like a repeating sequence, right? This is essentially the polynomial expression for ln 1 plus x. And maybe let's just try and do that for, maybe let's example 2, we'll just try and do that for ln x. And how will we do for ln x? Well, here we won't consider it about a is equal to 0, we'll consider it about a is equal to 1. But anyways, so what will be f of a? F of a will be ln 1, which is obviously 0. What will be f prime x? F prime x will be 1 by x, and f prime a would be obviously 1 by 1 is 1. F double prime x will be negative 1 by x squared, and needless to say, f double prime a will be negative 1. And once I do that, once I plug this back into the equation, I'll get nothing but f of x, which is nothing but ln x, and I'll get that as I'll basically get that as x minus 1 minus x minus 1 whole squared divided by 2 factorial plus 2 times x minus 1 whole cube divided by 3 factorial, and so on and so forth. Essentially, once you get this data, once you differentiate it maybe and find it at x equal to a, you just need to plug this back into the original equation that I given to you in the Taylor series, and then you get this expression. This is the expression for ln x. So maybe let me just write it a little more cleanly. I'll get x minus 1 negative x minus 1 whole squared by 2 factorial plus 2 by 3 factorial times x minus 1 whole cube, and this just goes on and on and on. So maybe if I just evaluate at x equals to 2, I'll get the value of ln 2, right? So what is ln 2? ln 2 will be nothing but 1 minus 1 by 2 plus 1 by 3 minus 1 by 4, and so on and so forth. And this is actually very important to know because it's related to our question. So all of this that I was discussing was kind of to like come down to the fact of ln 2. That's the entire discussion of Taylor and Maclaurin series is related to our question. Believe me, it is. And you'll actually see when I just write down the question. So what is the question? We need to evaluate the sum, right? There was some sum given. Yeah, we need to evaluate the sum. Let me just write this down over here. So we need to evaluate this sum. S is equal to sigma from k is equal to 1 to infinity of minus 1 raised to k minus 1 divided by k times another summation from n is equal to 0 to infinity of 1 divided by k times 2 raised to n plus 1. Okay, now believe it or not, this entire thing written over here is actually nothing but ln 2. Because once I like figure out this summation, once I just plug this summation into this, what will I get? Plug in k is equal to 1, you will get negative 1 raised power 0, which is obviously 1, right? Plug in k is equal to 2, you will get negative 1 raised power 1 divided by 1. Plug in maybe k is equal to 3, you will get negative 1 raised power 2 divided by 3, and so on and so forth, right? So this is nothing but 1 minus 1 plus minus 1 by 2, I'm sorry, plus 1 by 3 minus 1 by 4, and so on and so forth. So if you actually just plug this in, if you actually just find out the value of sigma, right, if you just maybe expand a few terms over here in this expression, you actually see that this is actually equal to ln2. This is just what we discussed over here. ln2, 1 minus 1 by 2 plus 1 by 3 minus 1 by 4. You're getting the same, right? This is plugging k is equal to 1, this plugging k is equal to 2, plugging k is equal to 3, you get exactly the same thing. So it is indeed true that this expression, that this thing over here, this thing is actually ln2. And that's it. This just simplifies the problem significantly, right? That signifies the problem significantly. It actually help you a lot, but that's the thing. That's the thing to know. Like I see this problem and I see that that's ln2, but is it worth substituting it right now? Maybe not so much, right? Maybe not so much. But it's a good thing to know that ln2 is nothing but the summation from k is equal to 1 to infinity of minus 1 raised power k minus 1 divided by k. Okay, maybe let's move on a little bit. Now, here's a little bit of an observation that I have. Right, here's a little bit of observation. When I see this actually reminds me of something. And you know what? Summation is actually reminds me of integral as well. So integral is nothing but big sigma. Right? Integral is nothing but the sum of areas of small parts. So it's essentially related to the summation itself. Big sigma is often referred to as an integral. Right? But if I just maybe notice that the integral of x is power n dx is nothing but x is power n plus 1 divided by n plus 1. Right? But if I maybe try to figure out the integral of x is power n dx from 0 to 1, that would actually be 1 by n plus 1. And that's actually pretty cool, because what's given over here, in the question they had this sigma from n is equal to 0 to infinity of 1 by k times 2 raised power n plus 1. So maybe if I replace this n with k times 2 raised power n, I can just kind of reduce this down to an integral. So essentially what I'm doing is I'm just reducing this sum is equal to sigma from k is equal to 1 to infinity of negative 1 raised power k minus 1 by k times sigma from n is equal to 0 to infinity, and then kind of replacing this with the integral, right? X times x raised power k times 2 raised power n dx from 0 to 1, right? Because instead of this k times 2 raised power n, if you would have just had n, you would have gotten 1 by n plus 1. But because you have this k times 2 raised power n, you would get k times 2 raised power n plus 1 with the limits of 0 to 1, obviously. Okay, that's great. And now whenever I see like multiple summations, when I see integrals, what do I think of? I think of maybe we can interchange these summations a little bit. Maybe we can do something about the integral or something. And actually, when the sum is convergent, right? Whenever the sum is convergent, you can actually bring this integral out over here. And this is actually a good thing to know. And this is only true whenever the sum is convergent, okay? But we know that it's convergent, so we can maybe bring this integral out over here. So this becomes the integral from 0 to 1 of the summation from k is equal to 1 to infinity. We just write it like this. N is equal to 0 to infinity. K is equal to 1 to infinity. And then we have this couple of things, right? Negative 1 raised power k minus 1 divided by k times this x raised to the power 2 raised to the power n whole times k dx, right? I kind of like simplified this to this, because anyway it does not matter because k gets multiplied by 2 raised to the power n, so it's pretty much the same thing. And you know, it's a good thing to know that the kind of expansion from ln1 plus x that we have actually studied, that is nothing but minus 1 raised to the power k minus 1 by k times x raised to the power 2 raised to the power n times k. This is actually the expansion of ln1 plus x, because if you just start plugging in the values of k, you would actually get what we had studied over here, right? The expansion of ln1 plus x, this one. If we actually maybe plug in the values of k over here, you would actually get this x minus x squared by 2 factorial and so on and so forth. Yeah, actually this just becomes x minus x squared by 2 factorial plus x cubed by 3 factorial minus x is power 4 by 4 factorial and so on and so forth. And this will obviously happen once you plug in the value of k, the summation, once you do that. But okay, anyways, moving on, so this essentially reduces our sum to this thing, right? Integral from 0 to 1, if we just write down the sigma from n is 0 to infinity of ln 1 plus x to the power n dx, right? Because this entire thing just becomes ln of this quantity, right? Ln of 1 plus this quantity. Okay, that's great. And after this point, it just becomes like a little bit easier. You just expand this. So 0 to 1, just open this sigma, right? You just start plugging the values of n. And when you do that, you'll just understand that this is nothing but the ln 1 plus x plus ln 1 plus x squared and so on and so forth plus ln 1 plus x to the power 4, and this goes on, and this entire thing dx, right? You integrate that. And there's just a property of logs that ln a plus ln b is nothing but ln ab, and once I apply that over here, I'll get the sum is equal to 0 to 1 ln 1 plus x times 1 plus x squared times 1 plus x to the power 4, and this goes all the way dx. Okay, great. So this just becomes 0 to 1. If I just start using the pi notation over here, I can just write this as ln of pi from n is equal to 0 to infinity of 1 plus x raised to the power 2 raised to the power n dx, right? I just use the pi notation, which is the multiplication notation, and again, if you just put n is equal to 0, 1, 2 and start multiplying the terms, you would essentially get this. So okay, that's great. Now let's move forward. Now once I just open this, right? Once I just open this, so I think I'll just demonstrate this actually. So what is this? What is this quantity? Pi from n is equal to 0 to infinity of 1 plus x to the power 2 to the power n. What is this? We start plugging in n is equal to 0, I get 1 plus x. Plug in n is equal to 1, I get 1 plus x squared. Plug in n is equal to 2, I get 1 plus x to the power 4, and so on and so forth. Right? And the multiplication is the pi symbol, the capital pi symbol. The sigma is the summation, this capital pi is basically multiplication. Okay, great. And believe it or not, once you open this out, you'll get nothing but 1 plus x squared plus x cubed and so on and so forth. You actually carry out this multiplication. I'll just demonstrate that for two things. So if we have 1 plus x times 1 plus x squared, you will get 1 plus x squared plus x cubed, which can be written as 1 plus x squared plus x cubed. Once you multiply that 1 plus x to the power 4, you'll get some other terms, right? You'll get terms up to 7 because the degree will be 7 plus 4, 5, 6, 7. You get all of these terms. So essentially, once you multiply this out, this entire thing or all of these infinite things, you'll get this entire infinite expression. So the sum essentially reduces to this entire thing gets reduced to the infinite expression ln of 1 plus x squared plus x cubed all the way up till infinity dx, integral from 0 to 1. And if you know the sum of an infinite geometric progression, that's nothing but a over 1 minus r, where a is the first term and r is the common ratio. Here a will be 1 and r will be obviously x. That's sum of an infinite GP, geometric progression. Right, so this sum essentially is nothing but 0 to 1 of ln of a, which is 1 over 1 minus x dx. And you can just write that as sum is equal to negative 0 to 1 of ln 1 minus x dx. And if I just maybe like replace this negative and just swap over these the limits, I'll get from 1 to 0 of ln 1 minus x dx. And after this is a really simple integral. You can use integration by parts. Integral u dv is equal to uv minus integral v du. And essentially, yeah, so you can just plug in maybe u is equal to 1 minus x, du will be negative dx, and so that essentially you will be left with sum is equal to the integral from 1 to 0 of ln u. Obviously dx is equal to negative du, and you proceed with this. So basically sum becomes basically the integral from 1 to 0 of maybe let's just replace the signs from 0 to 1 of ln u du. And again, once you just integrate this by parts, once you just use this formula, integral u dv is u minus v du. Once you just integrate this by parts, you'll actually get that the sum is equal to negative of u times ln u minus u, which is from 0 to 1. And once you plug in the individual values of u is equal to 0 and u is equal to 1 over here and calculate this sum comes to be negative of negative 1, negative 0, which means that the sum is equal to 1. So yeah, this quite an interesting problem actually. It was very lengthy. It took me like around 1.5 hours to solve this when I tried it for the first time, and it is lengthy and it is a little bit tricky, no doubt about that. But the takeaway is that these are some nice expressions using the Fourier series and Maclaurin series that you can generate. And it's good to remember, because until unless like you maybe practice this Fourier series a lot, it won't immediately click in your mind that what's given to us in the question, this thing is ln2, this thing is ln2, right? It doesn't necessarily immediately click. But maybe once you just expand this out a little bit, you'll actually see that this is ln2. And if you have seen the Fourier series many times before. And this obviously is a beautiful idea of that integral of x is power n dx, which is probably the first formula that you learn when you study integration. But yeah, you found this application on one of the last problems of the Putnam exam. So yeah, this is a really cool problem actually. And with this video, I actually kind of like I'm expecting that you do know a little bit of integration by parts and this kind of like the end steps of the integration. But yeah, if you study that, it should be pretty trivial for you. But regardless of that, I hope you really learned something from it, and let's move forward. Okay, so after this, you have certain book sessions for college mathematics, Introduction to Real Analysis, Principles of Mathematical Analysis by Rudin, Calculus Volume 1 and Volume 2 by Apostle, Topology, Contemporary Abstract Algebra by Galen, Topics in Algebra by Hurstein, Abstract Algebra by Dummett and Foote, Linear Algebra done right by Axler. Okay, so at the end, you have a similar but challenging problem, and I want you to evaluate the value of this summation. So again, over here also you need to use Taylor series. That's the only hint that I'll give you, because anything more and it will be too easy. And yeah, anyways, if you're able to solve it or if you make any progress on it, let me in the comment section. And until then, I'll see you in the next video. Thank you very much.
The programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.